The talk I'm going to present is a joint work with Lukasiewicz, who some of you may know, and it's about unification. So thanks Sarah for having introduced it already. So let's go nonetheless through the definition again. So if I have a set of equations, in this talk it will be the set of equations defining MV algebras. And a unification problem is a pair of a finite subset of variables and a finite set of equations with variables in that set. Now, I will often be lazy about the finite subset X. Maybe I will just the main important thing is that the equations have the variables in that finite set. So, for example, and this will be an example that will be of interest to us. It is this equation x join y join not x join not y equals 1, which we'll see later to be dual equivalent in some sense to the border of the unit square. And now a unifier for such a problem with variables drawn from a finite subset y of the set of variables is a substitution from x to the terms of y that makes all the equations, all the wannabe equations in the unification problem equal. So this means that for any I, if I substitute to SI, in SI x by sigma of x, I get a term which is equal to the same thing when I do it for Ti, modulo the equations in the theory. Okay, so let's see an example of a unifier for that problem. For example, if I want a unifier with variables in y, I can map x to y and y to y, and this is a unifier because this equation holds 1 join y join not 1 join not y equals 1. Modulo the equations of MV algebras. Okay, another example of unification problem that has no unifier is 1 equals 0, or also x equals not x. Okay. Now, okay, if I have a unifier, then I can compose it with a substitution, and I get another unifier, which is then said to be less general. So, for example, if I have a unifier that maps x to 1 and y to y, I can compose it with any substitution, for example, the map going from y to y plus y, and this will be a unifier. Okay? And now for the formal definition of what it means to be more general, I have two unifiers, sigma and sigma prime. Sigma is more general than sigma prime if sigma prime is obtained from sigma by a substitution. So if there's substitution theta from y to terms of y prime, such that for any x in x, well, sigma prime of x is, well, here it should be sigma on the right, sigma of x, where I substitute to each instance of y, theta of y. This relation defines a p-order, and we'll be interested in the postal reflection of it. Okay. So, just for example, is there a unifier that is more general than what we already have? Yes, I found it this via duality and then actually project back in the algebraic form. For example, if I map x to x plus y and y to x times y, I get another unifier. This is a unifier because if I do the first join the third one, I get, sorry, the first join the latter one, I get already 1. And E2 is more general than U1 because it is obtained via substitution. If I take U1 and I substitute to x1, sorry, if I take U2 and I substitute to x1 to y, I get the U1. Alright. So, okay, and if a unification problem has a unifier, then 4 situations may arise. The best one is if there's a most general unifier. It's called the unary, in this case the problem. Or the second one is, okay, maybe it's not unary, but there are still finitely many maximal elements such that every other element is below some of these. Or, or it's called infinitary if it's not finitary. So, but still every element is below some maximal one. And nullary if there, in the other cases, so if there's an element which is not below some maximal element. So if the maximal elements do not cover the whole set of unifiers. And the unification, so this is the situation arising for a specific problem, and the unification type of E is the worst possible unification type occurring among the unification problems with at least a solution. Alright, so yeah, Mara and Spada proved that the unification type of Lukasiewicz logic is the worst possible. It's nullary, as already mentioned by Sarah in the previous talk. And they, to do so, they executed a chain which is, what's the terminology, final or cofinal? I don't remember. A chain ordered as omega, such that every unifier is below some elements in the chain. Okay, and they prove it via duality. Now, okay, now comes the interesting bit for this talk, is that this chain of unifiers had used more and more variables in the solution, right? So the problem had used 2 variables. This was the problem, and the chain of unifiers used more and more variables. And so the question that already Magla and Spada posed was, okay, but does the unification type maybe improves if we take a fragment of Łukasiewicz logic where we only take finitely many variables? Okay, let's see what was known and what was not known. Okay, well, the trivial thing is that the unification type restricted to 0 variables is nullary. And Luca and Enzo proved that the unification type restricted to 1 variable is finitary. Okay. In general, you may have two maximal solutions. And they conjectured that for any n greater or equal than 2, the unification type is still nullary. So they conjecture that although in their proof they used this chain of increasing variables. Still, if we bound the variables, still we get the worst possible type, that is nullary. And the main result, our main result is that it is correct. This conjecture is true. So the unification type is truly nullary. So they were right. Okay, and the reason is that this problem is still nuts, so of nullary unification types. Still the same problem, we can say. Okay. Yes, so how do we do? We prove that there's a unifier, for example, the one I showed you before, that maps x to 1 and y to y, that is such that any unifier more general than it in and that uses at most n variables with n greater or equal than 2. Any such unifier admits a strictly more general one. And so it is not below any, sorry, it is a strictly more general one that still uses at most n variables. And so we don't have a maximally general unifier above it. Okay, and so although we solve the problem as stated in their paper, working on it, we realize that okay, the variables in the problem and the variables in the solution are maybe pretty unrelated. So maybe we may further refine the problem by specifying what are the number of variables that we are allowing in the problem and what is the number of variables allowed in the solution. So, okay, we have a whole table of problems for which we might ask the unification type. So, okay, here we have the variables allowed for the problem, and here the number of variables allowed for the solution. And so the question is, what is the unification type of Łukasiewicz logic restricted to n variables for the problem and n variables for the solution? So okay, it's trivially unary for, it's unary for, let me go back. So the original question was to fill in this diagonal. Okay, and what was known is that okay, it's unary for m equals n equals 0, and it's finitely for n, and we show that all the other things in this diagonal are nullary. And then we ask ourselves, oh, what happens in the other cases? Okay, okay, the most, let's say, the non-interesting bits are these columns, when n equals 0 and n equals 0, which are finitary or unitary. Already Manuel Spada proved that this is finitary, the n equals 1, at least their argument shows that it's finitary. And what we prove is that whenever both m and n, both the variables for the solution and for the problem are greater or equal than 2, then we get a nullary type. And still, okay, there's a column here, which was really frustrating, and it's open. We don't know. Yes, it's open problem. All right, and it's frustrating because there's just one variable for the solution. It should be so easy. Okay, let's see a bit the techniques in the proof in general for all the thing I'm happy about. So this nullary and this also this finitely one. Actually, let's see for the nullary. Well, we use the duality presented by Mara and Spada between finitely presented MV algebras and rational polyhedra. And we use the fact that free MV algebras the free MV algebra on n generators dually correspond to the hypercube 0, 1 to the n. And so here we can translate all the unification problems and the unifiers via duality. In translating the duality, a unification problem consists of a natural number m and a rational polyhedra in 0, 1 to the n. And as I mentioned before, the dual of this problem is the order of the unit square. And the unifier is a Z map. A unifier with n variables is a Z map from the nth power of the unit interval to the polyhedron P. So a unifier for this would be, for example, in one variable, when I first represented the unifier that maps x to 1 and y to y. Okay, these would be would map. Okay, this is only in the variable y. This would map the line to this segment here. This is the Z map. Okay. Okay, and a unifier. Okay, what does it mean that a unifier is more general than another one? Okay, if I have two unifiers, f and f prime, the one above is more general if there is a comparison morphism going upwards. Where here by comparison morphism we mean a Z map, which if we recall, for example, from Lukas' talk, is a piecewise, a finely linear map with integer coefficients. Okay, and let's see essentially why it is nullary also when we restrict to two variables for the solution for the problem of the boundary of the square. Okay, let's take as a unifier the map which I call left, which just for maybe it's not clear what it does. It collapses everything to the left side. Okay, so every element is mapped to the left. And so I draw also in blue the image of this map left. Now, this unifier is less general. There's of itself. I put it here, and you see, if I take the identity, I get a commuting triangle. So this one on the top is more general. Okay, but now I can also use, instead of the identity, left. And now if you see, this diagram still commutes. And the image now is just the image of this morphism going up. Here also. The image of this map is just this. And so it's important that this map is non-surjective.
Is left supposed to be right?
Yeah. Right, thanks. Right. Exactly. Everything is right. Thank you very much. Thank you very much. Everything is right. Everything was wrong. Okay, first of all, the reason, okay, now that it's surjective, if I modify this function here on this region, then this triangle will still commute. But if modifying this here will allow me to get something strictly more general than this map here. For example, if I find a map whose image is bigger than the image of this, that's a way to clearly see that this is strictly more general than this. So for example, I can take as morphism the diagonal that maps every element here essentially to the, it goes along the diagonal until it hits one element in this border. So now this triangle still commutes, but now this up above is more general. Okay, so and similarly, and actually, for example, any unifier more general than right will have this property that I still can find something strictly more general than it using a similar trick. And so, for example, this problem doesn't have any unifier in two variable more general than it that is maximally general, because it will always have something more general. Okay, so now here, why this works? Well, first of all, here to find this non-surjective map, this right map, we use the fact essentially that the square has one dimension more than the border of the square, and so it's highly non-injective. The fact that it's highly non-injective means that, for example, this element has a fiber something quite big, and so I can map this fiber just to a unique point here and create a lot of space where I can work with. And finally, second thing is we were able to create something strictly more general because we said, okay, let's just create a map whose image is bigger. Now, maybe once you complete the four sides of the square, maybe you might say, oh, how can I create something with bigger images? Well, but then use the argument which Marta and Spada already used, that essentially a continuous function from the square to the border of the square is essentially the same thing as, since R is a cover of the square, is essentially the same thing as a continuous map to R, which allows us to have infinite space to work with. I can always create a map whose image is bigger, not here, but in the cover of the square. Okay, so just to sum up, we have the question was what is the unification type of Lukasiewicz logic restricted to m variables for the problem and n for the solution, and we filled these all these pieces for n greater or equal than 2 and n greater or equal than 2. Some cases were already known, finitely. I think if you come up with some idea how to solve this open problem, I will be very, very happy. Okay, thank you very much.